Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be adding powers of I with some coefficients. We have 1 plus 2i plus 3i squared plus 4i to the third power all the way up to and including n plus 1, the quantity n plus 1 times I to the power n. And we're going to find the sum in terms of n. I'll be presenting two methods and let's see how this goes. Now, for my first method, I kind of want to write more terms, obviously, so let me go ahead and give you a little bit more than this, but I hope you got the idea because I gave you the nth term, or I should probably say the general term. 1 plus 2i plus 3i squared plus 4i to the third power, and then my last term is n plus 1 times I to the power n. Notice that we have a pattern. The power of I is being increased by 1, and that just becomes the coefficient. So I to the second is being multiplied by 3. Makes sense? 2 plus 1. Okay, so to find the sum in terms of n, actually, it's not very easy and straightforward in my opinion. Especially you're going to realize something interesting about the first method, and then the second method will hopefully make everything more clear. But anyways, let's get started. For my first method, I'm going to go ahead and try to get a pattern. Let's go ahead and add these now terms. Maybe the first 4, how about that? Because 4 is a good number. If you're dealing with powers of I, and when you do the 4 consecutive terms, you should get a pattern, because I to the fourth power is 1, and I to the power 1 is 1, I to the power 1 is I, second power is -1, so on and so forth. Anyways, let's go ahead and expand this. 1 plus 2i, I squared is -1, so that's going to give me a -3, and this should be a -4i. And then, now, this is the first 4 terms. To get a better idea, obviously, we do need more terms. And let's go ahead and continue, but let's write them in different rows. So the next term you're going to get is 5i to the fourth, and that is going to be a 5. And then maybe I should write it on the side so it's a little easier to calculate, so we don't have to do it mentally. And then it should end in 8i to the 7th. So 5i to the fourth is 5. This is going to be the same as I. And then this is going to be the same as I squared, which is -7. And this should be the same as I cubed, which is -8i. Now, something interesting that you should notice, if you simplify each of these, the first one gives us -2 minus 2i. And let me tell you what I was expecting to get. I was expecting that the terms would increase or maybe decrease negatively, right? But that didn't happen. It's so kind of surprising, right? -2 minus 2i. We're actually getting the same thing from each quartet. That's an important concept. So I call each group of 4 terms a quartet, and we're going to be looking at each quartet because they always have the same sum, provided that you start with 1. If you don't, then you're going to get something different. Okay, let's go ahead and write one more. The next one is just going to be, or I can just give it to you, 9 plus 10i, and then -11 minus 12i. Hopefully you get the pattern. We have 1, 2, 3, 4, but then you kind of attach the powers of I, and then 5, 6, 7, 8, and then 9, 10, 11, 12. You get the idea? And that's why we probably get the same thing over and over. Of course, this is going to continue until we hit n plus 1 times I to the power n. So how does that work out? So here's the thing. Since I know the sum of each quartet, I can kind of split it up into cases, such as, since I work in groups of 4, let's think about it in terms of mod 4. So I'm going to say, okay, suppose n is equal to 4k minus 1, which implies that you're going to be dealing with k quartets. Because if you really think about it, for example, if k is equal to 1, you only have 1 quartet, n is going to be 3, so you're going to end up with I to the third power, which actually gives you the end of the first quartet. Make sense? So n equals 4k minus 1 refers to k quartets. And then from here, s, which I call my sum, -2 minus 2i multiplied by k. Because each quartet gives me -2 minus 2i. And if I have k of them, then the sum is going to be k times that. Make sense? But this is just one of the cases, and I'm not going to finish all the cases, but maybe I want to show you one more, and hopefully you can finish the rest. What happens if n is equal to 4k? In other words, we have k quartets plus 1 term. Make sense? So in this case, your sum is going to be very similar because obviously you're going to have the terms, or the sum from the k quartets, plus the next one. And notice that when your last term is like something like 4i to the third, the one that follows is going to be 5i to the fourth, which is 5. But where does 5 come from? It's actually 4k plus 1. Remember, for k equals 1, you should be getting 5. What happened to I to the fourth? It's equal to 1, so I don't need to worry about it. Make sense? So by adding every time the new term, you should be getting the sum as a piecewise defined function. But guess what? This is too complicated. So we have something better, which is called the second method. Okay? I know it's kind of like torturous or maybe circuitous to give you the first method first, but it's like no pain, no gain. Okay, so here's the second method. To find this sum in a much better way, in a smarter way, obviously, right? I want to consider this as a series. So instead of I, I'm just going to use X. Make sense? So that's kind of like a rare practice, but it's very helpful. If you replace a constant with a variable, you know, that's kind of weird, but it's the other way around usually, but it's usually helpful. So this is one of the problems whose general case is easier to solve than the specific cases. Make sense? Okay, I hope it does. And I'm going to call this sum maybe S, or actually let's not call this sum S because S is going to be something else. Okay, anyways, let's leave it at that. I want to find this sum in terms of n, and of course in this case it's going to be in terms of n and x both, right? How do I find it? Good question. And here's what you can do. Now this sum is going to be called S, and this sum is something you should be familiar with. Let me write it down. S is equal to 1 plus x squared plus x cubed all the way up to, guess what? X to the power, not n minus 1, not n plus 1. Do you know why I ended up with x to the power n plus 1? So I have like n plus 2 terms. Why would I want that? Because we are about to do something special to this expression, which is called differentiation. Yay, calculus is awesome, right? So if you differentiate this expression, by the way, we could also write this as s of x, meaning that this is a function of x. Sometimes people are going to put a little n here, s sub n of x, which means n is also in the equation, okay? That represents the last term. So if you differentiate this, derivative of 1 is 0, derivative of x is 1, and then differentiate it, keep doing it, you're going to get something like this. And this is just awesome. You know why? Because it gives us the original sum, which we are trying to evaluate. Wait a minute. It's not. Is this something I want to evaluate? Well, sort of. It is, because look at this. If I can find this sum, I can also find this sum, because all I have to do is replace x with I. That's what we're going to do. Make sense? So how do you evaluate it? Well, we do know what S is. What is it? It's the geometric series, and it's finite. So we have a formula: 1 minus x to the power n plus 2, increase the highest power by 1, and divide by 1 minus x. Easy, right? Something you should memorize. Now, I got to differentiate it. So how do I differentiate it? Using the quotient rule. Let's do it. The derivative of the top is minus n plus 2 times x to the power n plus 1. You have to reduce the power. And then multiply it by the bottom. And then minus the derivative of 1 minus x, which is negative 1. That's going to change the sign. And times the top function, which is 1 minus x to the power n plus 2. Awesome. This is the derivative of s, and of course the denominator squared. This kind of looks complicated, but don't worry about it. It's going to simplify. In this expression, I would like to replace x with I. In other words, I'm trying to evaluate s of I, or I should say s prime of I. Okay, so here's what happens when I did that. When I do it, I should be getting negative n plus 2, n is not going to change, times I to the power n plus 1, multiply by 1 minus I, and then plus 1 minus I to the power n plus 2. Remember, we're only replacing x with something, which is I. So that's my sum. This should be the answer in terms of I or n, right? But how do you simplify it? Here's the thing. When you square this expression, let me go ahead and distribute this over 1 and minus I. When I distribute over 1, it should be by the way, that minus sign should be outside, not like that. Here we go. And then when I distribute it, it's going to be negative n plus 2 multiplied by I to the power n plus 1 and multiply by negative I. That's going to give you plus n plus 2. And the power of I is just going to increase. That's going to be n. Oops. I was supposed to. Okay, here we go. Multiply this by I to the power n plus 1 times I to the power. By the way, it's not n plus 2, n plus 1. It's n plus 2. Times I to the power. Remember, I'm multiplying it by minus I, so it becomes a positive, plus the power of I is increased. Okay, here we go. And then I should be adding 1 and then subtracting I to the power n plus 2. And then 1 minus I squared is just going to be negative 2I. Now, to take care of this, I should multiply the top and the bottom by just I, because that'll give me positive 2 here. Nice. Let's go and distribute the I. That's going to give us something interesting. But first, maybe I'll just distribute it. Anyways, negative n plus 2 times I to the power n plus 2, and then plus n plus 2 times I to the power n plus 3, plus I minus I to the power n plus 2. I mean plus 3, because that is the powers are added. Okay, here we go. Now, here's what I can do. I can combine these two things because they have the same power of I. N plus 2 minus 1 is n plus 1. So let me write that first. N plus 1 times I to the power n plus 3 minus n plus 2 times I to the power n plus 2 plus I divided by 2. And guess what? That should be the answer. If you want, we can go ahead and check it out for a particular value of n, which in this case I would use n equals 3, because that gives us the first quartet. If n is equal to 3, you're going to get 4 I to the power 6 minus 5 I to the power 5 plus I divided by 2. I to the 6 is the same as I squared, which is negative 1. So that's going to give me negative 4. I to the 5th is the same as I, so it's going to give me negative 5I plus I divided by 2. Negative 4 minus 4I divided by 2. That should be negative 2 minus 2I. Yay, we got the right answer. Awesome, we're happy. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.